Hi, everybody. Today, we're going to be talking about inner products and inner product spaces. So basically, we've been talking about vector spaces. And last week, we talked about moving from one vector space to another by using linear transformations. This week, we're going to talk about new ways to combine objects within a vector space already. So our vector space has an addition operation and a scalar multiplication operation. But what about a type of multiplication with objects that are in that space? So that's what we're going to define our inner product to be. It's going to be kind of like a multiplication-ish sort of thing on two elements in your vector space. But the answer is not going to be an element of your vector space. The element's going to be a scalar value. So let's define what we mean by inner product, and then we'll work through a couple of examples, some of which may seem very familiar to you. So an inner product on a vector space V which we're going to write using angle brackets. So this would be the inner product of U and V, is a function that assigns a real number to every pair of vectors U and V, so that the following axioms are all satisfied. And we're going to have a list of 5 axioms here. The first one is that the inner product of U and V is a real number. The second one is that it commutes. So the inner product of UV is equal to the inner product of VU. The third one is kind of like sort of like an associative distributive kind of thing. It's a reordering of stuff. So we're going to have the inner product of U plus V and W. That's going to equal the inner product of UW plus the inner product of VW for all U, V, and W and V. If we have a scalar multiple of U and we take the inner product of that with V, that's the same as taking the inner product of just U and V and multiplying it by that scalar value. Once again, for all U and V in V, and for all K in R. One thing in particular to notice about this one, be careful, it's not like distribution. So notice that the K is applied only to the U, it doesn't get applied to the V. So you don't like distribute the K to each of those, okay? It only goes to the first one. And then the last one is that the inner product of a vector with itself is always greater than 0, so long as that vector is not the 0 vector. So if I take the inner product of something with itself, I get something that is non-negative and not 0, actually. All right. So let's do an example of an inner product you're already most likely familiar with, the dot product. So I'm going to erase the board and then we'll do an example using the dot product. And in particular showing that the dot product satisfies all 5 of these axioms. So to help us out, I've relisted those 5 axioms over here on the side, kind of an abbreviated format. And what we're going to do for this problem, for this example, is we're going to show that the dot product u dot v is an inner product on Rn. And just a reminder of what the dot product is, you take the ith element of each vector, multiply them together, and then you add them up, right? So just as an example off on the side, maybe I'll do that over here. If I'm in R3 and I have something like 2, 1, 3, that I'm going to dot with something like 1, 0, -1, I would do 2 times 1, 1 times 0, and 3 times -1, add them all up and get, in this case, -1 as my answer. So that's an example of the dot product in R3. So what we're going to do is we're going to prove that the dot product satisfies all 5 of these axioms, no matter what dimension of R we're looking at. So let's start out with the first one. I have a table in the way here. I'm just going to move it so I don't hit it. I'll hit the lamp instead. That's fine. So for the first one, we're going to find a marker that will write. Let's try that again. So for the first one, better, we're going to show that the dot product between 2 vectors is always going to be a real number. So I'm going to start out with u dot v. Well, that's equal to the sum of the ui's times the vi's. Now, in this case, I guess I'm just going to put like a little note on the side here. Ui is an element of R, and vi is an element of R, because u and v are elements of Rn, so their components have to be real numbers. Then I would say that ui times vi has to be an element of R, because the product of real numbers is a real number. And then the sum of the ui's and the vi's has to be an element of R, because the sum of real numbers is a real number. So, and just for limited space, I'm not writing that down, but if I were doing a full proof, I would absolutely write that down. So here I would write down because products of real numbers are real. And here I would have because sums of real numbers are real. But for space purposes, I'm going to abbreviate it in this manner. So that's it. We proved the first fact that the dot product has to be a real number. Next, we want to show that the dot product commutes. So if I have u dot v, I'm going to get the same as v dot u. So for my second one, I'm going to take u dot v, and I'm just going to apply the definition here. That's the sum of ui, vi. Well, because the ui and vi are real numbers, they commute in their multiplication. So this is the sum of the vi's, ui's. And that's because multiplication is commutative in the reals. But now if I look at this and apply my definition of the dot product, this is the same as v dot u. That's by definition of the dot product. So there we go. It's going to commute. So next we'll do the third one. I might not have enough space here. We'll try and give it a go. So for the third one here, we have to show that if I have u plus v and I dot that with w, I get the same thing as u dot w plus v dot w. So we're going to start out by saying if I have u plus v and I dot that with w, let's apply our definition of the dot product on this expression. Excuse me. So that's going to be the sum of the ith element of u plus v times the ith element of w. And that's just by our definition of dot product. Now, if I have two vectors, u and v, and I add them, the ith element of that is just the sum of those two ith elements. So this is the sum of ui plus vi times wi. And that's the definition of matrix addition, or just more broadly, addition in Rn. And then these are all real numbers now. So since they don't have the bars over them, they're not vectors. These are just real numbers. So we can distribute wi to each of those. So this is the sum of ui wi plus vi wi. And this is our distributive property. And this is nice now because we have a sum of a sum. So using commutativity and associativity, we can split that up into two summations. So this is the same as the sum of ui wi plus the sum of vi wi, right? So I'm just going to call this a summation property. But you could also say that's because of associativity and commutativity of real number addition and multiplication. And now we have some good news because ui wi, that's going to be the same as u dot w. And the sum of the vi wi is y, that's just v dot w. And that's what we needed to show. We needed to show if we were adding here in our first grouping that we can split it up and add across these two. I guess I would say that's the definition of dot again. So what I would recommend, now that we've gone through 3 proofs of using the dot product and showing that the dot product is satisfying these first 3 properties, pause the video here and take a moment and work through these other 2 proofs and see if you can prove these 2 properties for the dot product. Once you think you got it, unpause, and then we'll walk through it together and we'll see how you did. All right, have you taken a moment to walk through the proofs of the last 2? If you haven't, I really do recommend you pause and work through it so that you can kind of practice thinking about how you would go about solving a proof. And then let's work through it now. So I'm going to start out with a scalar times u, right? Because that's what we're starting out with here, ku dot v. We're doing this here. So by our definition, this is going to be the sum of the ith element of ku times the ith element of v. But when we multiply a vector by a scalar, its ith element is just the ith element of u times k. So this is going to be the sum of kui times vi. And that's by our scalar multiplication. And because of associativity, I don't need to put those parentheses around the product. So I can just write this as kui vi. So that's the associativity of real number multiplication. Now, we're summing over I, but k doesn't depend on I. K is going to be the same value each time. So this is like 3 times a thing plus 3 times another thing plus 3 times another thing, etc. So we can factor 3 out of that whole summation because of distribution. So this is going to be k times the sum of ui vi because of the distributive property. But the sum of ui vi, why, that's just u dot v. So this is going to be k times u dot v, which is what we needed to show here. And again, that's our definition of dot. All right, so that's our proof for 4. This one's fairly similar to the previous proofs that we had been working on. the proof for the last one for number 5 is a little different. So we're going to start out for that one, as we've been doing, by starting out with u.u. and seeing what we got here. So when I do u.u, that's going to be the sum over I of ui times ui. That's our definition of dot. Now, these are the same value, so I can rewrite that as ui squared. So this is the sum of ui squared. And I'm going to put just that's greater than 0. That's going to take some explaining why that's going to end up being greater than 0. So the reason that it's greater than 0, I'm going to do kind of like what I did for the first proof that we did, where I write some notes out. So if u is not 0, right? So we're doing this for a vector that's not the 0 vector, then ui is not 0 for at least one I, right? In other words, if I have my n by 1 vector, at least one of the coordinates is not 0, because I'm not the 0 vector, right? At least one. Could have more, but at least one is all I need. So because of that, then I'm going to say that I'm going to pick that particular I here. That value has to be greater than 0, since any real number squared is greater than 0 if the real number is not 0. So if I take 7 and square, I get a positive. If I take -7 and square, I get a positive. The only time I don't get a positive when I square a real number is if that number is 0, because then I would get 0 instead. So we're picking in particular here an instance where we have something that's not 0, so we get something greater than 0. So this summation is going to be greater than the sum of this particular thing, because all we're doing is we're adding either zeros or positives. So the summation of ui squared is a sum of zeros, possibly zeros, and positive numbers. So it is positive. Right? There's at least one positive value in there, so it's got to be bigger than 0. And I'm not going to be subtracting anything, so I won't be going lower than 0. So here we have that this is satisfying this condition here, that we have to be greater than 0 if we are not 0. All right, so that's our proof that the dot product, the one that we know and love from Rn, is indeed an inner product. So now let's look at a few inner products for other spaces that we've been talking about with our vector spaces. So in particular, we've been talking about spaces where our vectors are matrices, or spaces where our vectors are polynomials. So let's examine some definitions of inner products on those spaces. Wait, before we do that, we have one more definition to talk about. I forgot that we had to define this before we can do those inner products. So this is going to be the definition of a trace, which I think we've seen in some homework, but let's define it formally now in the notes. So the trace of an m by n matrix A is, and the notation that we're going to use is TR of A. So this is going to be our trace of A. That's going to be the sum of the ith entry. In other words, i.e., this should have been n by n, sorry about that. We need a square matrix because the trace is the sum of the diagonal entries of a square matrix. So that's how we can find that. So, okay, so now that we have this definition, let's look at a couple properties of trace, and then we'll see how this applies to our inner product stuff. Alrighty, so theorem 12 is some properties of trace. So if I have two n by n matrices, A and B, then the trace of the sum of the matrices is the same as the sum of the traces of the matrices. And if you think about this, this kind of makes sense, because if you have your two matrices and you add them, think about what's happening along that diagonal. So you're just adding those diagonal entries. So if you find the trace of the first and the trace of the second, it's the same thing as if you find the trace of the sum of each of those diagonal entries. We have a similar thing going on here in property 2, where we have the trace of Ka is the same as K times the trace of A. That's basically our distributive property in action here for real numbers. And then 3 is a little bit less intuitive, but the trace of a product is the same as the trace of the reverse product. So remember that matrix multiplication does not commute, but the trace will be the same if we change the order of multiplying those matrices. So all of this is important because our common inner products, our first one is the dot product, which we went over in the last example. And the second one now is if I'm in MMN or MMN, I can define an inner product by using the trace. Now, in order to use the trace, you need to have a square matrix. And if I look at my subscripts here, we have MN. So we do not necessarily need to have square matrices in order to find this inner product. And we'll see why when we do an example of this. So one thing in particular that's going to be really important here is notice that I don't have the trace of AB, but I have the trace of AB transpose. We need to make sure we're taking the transpose of one of the matrices so that the dimensions line up so multiplication is possible. Okay, so that's 2. 2 is our trace of the product of the matrix, and the second one is transpose. And then the third common inner product we'll be looking at is if we're living in Pn, what you do, it's very similar to the dot product actually. You multiply corresponding coefficients and then add them up. So like I said, we're going to work through an example of applying these different inner products so we get a sense of what they're like. So let's do a couple examples of this together on the board. Alrighty, so we have 3 common inner products from that last note. So we're going to do an example of each one. So for the first one, we're going to be living in M32, and we're going to find the inner product of two 3x2 matrices A and B here. So to do that, so this is part A, I need to, in order to find the inner product of A, B, that's going to be the trace of the product AB transpose. So let's find AB transpose first, and then we'll find its trace. So A is going to stay the same. So we're going to have 1, 2, 4, -1, 0, 4. And then for B, we're going to find its transpose. So instead of having a 3x2, we're going to get a 2x3. So we get 1, -1, 1, 1, and 0, 2. Remember, in the transpose, the rows become columns and the columns become rows. Then we're just going to multiply like usual. So I'm going to have 1 plus 1, which is 2. Then I'm going to have 1 minus 1, which is 0. And then I have 0 minus 2, which is -2. And we're just going to continue multiplying. So I'm going to get 2, 2, 0. 4 minus 4 is 0. 4 plus 4 is 8. And 0 plus 8 is 8. So if I multiply A times B transpose, I'm going to end up with this 3 by 3 matrix. And the trace says find the sum of the diagonal entries. So this is going to be 2 plus 2 plus 8, which is 12. And there we go. So that's our first example of finding the trace in the land of matrices. For B, now we're living in R4. So the inner product here is going to be our dot product. So that just means multiply those corresponding entries and then add them all up. So we have 1 times 0. I'm going to do V1 dot V2 here. 1 times 0 is 0. -3 times 3 is a -9. 5 times 2 is 10. And 2 times -6 is -12. And when I add all of that together, I think I get a -11. Now, don't be concerned here that we got a negative number. You can have a negative number as your inner product. The only time you need it to be positive is if you are inner producting with itself, right? So if I had V1 and the inner product of V1 with itself, then I need to end up being positive. But if I'm just doing the inner product between any two vectors, I could get a positive or negative or even 0. And then lastly, now we have some polynomials. We're living in the land of P2. So the inner product of the two polynomials is we're just going to multiply the coefficients of the same degreed terms together. So for instance, if I look at the x squared terms in both of these, this has a coefficient of 1, as does this one. So 1 times 1 is going to be 1. Then I have a -4, and there is no x term here, so that means its coefficient is 0. So I'm going to have +0. And then for the constant term, I have 4 times -1, so that's a -4. So I end up getting -3. All right, so there you go. That's our inner product for the polynomials. So you can see why this inner product for polynomials is kind of similar to the inner product for real vectors, because in the real vectors, when you do the inner product, you're multiplying corresponding things together and adding them all up. And that's what we did for the polynomials. We multiplied corresponding things together and added them all on. And in fact, that's also what we did here for our matrices. If I want to think about this 2, where this 2 came from, it came from these two being multiplied and these two being multiplied and adding them up. That's where this 2 came from. If I want to see where the second 2 came from, so this 2 here came from multiplying this 2 times this 1 and adding it to this 0 times that 1. So we multiplied those corresponding pieces. And this 8 came from doing this 4 times this 0 and this 4 times this 2, and then adding them up. If I look at what that means in terms of these two matrices, okay, it's a little bit obscured because we had to do this transpose, but really what we did is we multiplied these two times these, and these, and added all of those together. So we took these two matrices and we multiplied their corresponding pieces and added them up. So that's not going to be the case for every single inner product. Just like when we defined our vector spaces, you could have different definitions for vector multiplication and addition that would define your space, sometimes a little bit weirdly. You can do the same thing for inner products. You can get some weird looking inner products happening as long as I satisfy those 5 axioms. But in this case, these common types of inner products, they all have the same essence, the same basic idea behind them. So before we end out this video, we're going to do some properties of inner products and maybe a couple of proofs. I don't know if we'll prove all of them, but we'll talk through them. So I'm going to erase the board and let's prove some properties. All right, so theorem 13 has 4 properties of inner products. So let's walk through them. So if I have the inner product of u and v plus w, that's the same as the inner product of u and v plus the inner product of u and w. So this property looks super similar to number 3 from our definition of inner products. So the main difference being here, I'm adding v plus w. So I'm adding like the second vector that's a part of the inner product. And here we added the first vector. So I'm not going to work through the proof of this one. It's very straightforward. Basically, what you do is you take this, you apply this definition. So you know that it's commutative. So you can rewrite this so the summation is first. Then you can split it up into this, right? So then you have something of this nature just with v, w, and u here. So you can apply this part of the definition. And then because we're commutative, you can switch the order of things again to get it to be uv and uw. So that's the main idea behind it. And the second property, same game, because now property 2 is super similar to number 4 from our definition, where we had ku and then v. Here we have u and then kv. So same thing, you use the commutative portion of our inner product to switch this order to end up with this, and then we can end up with that because that's actually our definition here. So the one that's a little different that I'll walk through the proof for is 3, because here we don't really have anything that involves the 0 vector directly. So let's walk through that. So if I prove the third one here, let's start out with the inner product of v and 0. So the only thing we know, right, is this information here. We don't know this is the dot product. We don't know what it is. Could be any inner product. So because it's an inner product, we know it satisfies these properties. So what we're going to do is we've got to try and figure out a way to get this 0 in terms of some other vector. So I'm going to rewrite this as v and then v minus v. So in our vector space, we know that a vector minus itself is going to give us the 0 vector. So we can rewrite it in this manner. Now, we also know that when I'm doing this subtraction, that's the same as adding negative 1v here. So I'm going to rewrite it in that manner. And now we're in a situation from this theorem that we are in up here, where we have a single vector in this first piece, and then we're adding 2 vectors in the second one. So I can split this up into the sum of 2 inner products. This is going to be the inner product of v and v. And then this is going to be the inner product of v and negative 1v. So that's by property 1 above. Next, because I have this negative 1 here, this is a value of r, it's a real number. So I can factor that out front. Okay, so now what I'm going to be doing is I'm going to be using this property 2 to help me out here. So this is the inner product of v and v plus negative 1 times the inner product of v and v. And this is property 2. Now remember that the inner product is always a real number. So I have a real number plus negative 1 times a real number. So I can rewrite this addition of negative 1 times as subtraction. So this is the inner product of v and v minus the inner product of v and v. And now I have a real number minus itself. So I'm going to end up getting 0. So there we go. So if you take the inner product of a vector with 0, you're going to end up getting 0. So what we've done here is we've established this first piece of this equality. We know that the inner product of v and 0 is the same as the inner product of 0 and v because of the second part of the definition, right? So we are commutative with our inner product. So we know that these two are going to be the same thing. So this part is just sort of inherited from that commutative feature here. And then, so that'll just be the one piece of this that we prove, I think, today. 4 is kind of similar, a little bit of similar trickery. You have to use a combination of this information here and this 5th property here to show that if the inner product is 0, that means that vector itself had to be 0. So yeah, so I think we're going to stop here with our inner products. In the next video for this week, we're going to apply this inner product to talk about the norm of a vector. So in other words, we've been able to talk about adding or subtracting vectors. Now we want to talk about the length of a vector. So the inner product is going to be how we define the length of a vector, and we'll do that in our next video. So I hope you have a wonderful day until then, and yeah, I'll see you soon. Bye.